Good morning, this is your stats sensei, Mr. Spensei, and we're going over a pre-quiz. All right, our scenario is just weed. Tumbleweed, commonly found in the western United States, is the dried structure of certain plants that are blown by the wind. Kochi is I thought it was kochia, but whatever. Kochi is it's a type of plant that turns into tumbleweed at the end of summer and is a problem for farmers because it takes nutrients away from soil that would otherwise go to more beneficial plants. Scientists are considered that the cochia plants, there it is with the resistance to the common herbicide glyphosate has changed over time. There are millions of cochia plants treated with glyphosate in both 2014 and 2017. Millions, that's a lot. In 2014, 12 out of 63 randomly selected plants were resistant to glyphosate. Hey, they were randomly selected. In 2017, 21 of 57. So we have two different random samples, 12 out of 63 and 21 out of 57, and they're both randomly selected. All right, so we have two independent random samples, and they ask us to create a 90% confidence interval for the difference in proportions. So we know right away we might as well fill out our C level, that's 0.90. We'll come back and calculate Z star at a later date. Well, what do we have? 12 out of 63. 12 out of 63 were resistant. And then in 2017, you know what? I'm going to label this as 2014, and this is 2017. In 2017, it was 21 out of 57. So let's go ahead and get our p hats in there. So this is going to be 12 out of 63. This is going to be 21 out of 57. So 2 divided by 63 is 0.1904. And 21 divided by 57 is 0.368. That is a big percentage difference. 19% versus 36%, almost double. All right, so we're running an entire test, which means we need to define our parameters. And we have two groups. So let P1 equal the true population proportion of cochia that were resistant in 2014. Let P2 equal the true population proportion of cochia that were resistant in 2017. So this one here is 2014, this is 2017, and we can go ahead and start running with our conditions. First off, random sample. Random sample. And the first random sample was of 63. And that was given. This was a random sample of 57. And that was also given. Number two, we had two independent samples. 2 independent samples. And that was given. Two independent samples given. All right. Number 3, we do have to do the n is less than 10% because it was random sample. Random assignment, we don't have to, but here we do. So our sample size was 63. So n equals 63. 63 times 10 equals 630. And that's less than, what was our population size? Oh, there were millions of plants. Well, that's less, 630 is definitely less than millions. All right. Number 3, for the other one, n equals 57. 57 times 10 is 570, and that's less than millions. So this also meets. So we're good to go so far. Number 4. All right, we're different than a hypothesis test. Hypothesis test use p hat c. We use n1 p hat 1. n1 times 1 minus p hat 1. Over here is going to be, for number 4, is going to be n2 times p hat 2 and n2 times 1 minus p hat 2. Well, n1 we said was 63, and this was 19.194. So this is 63 times 0.1904, and we know that that equals 12. And that's greater than 10, not by a lot, but it still qualifies. And then we have 63 times 1 minus 0.1904. And that's going to equal, let's check it out, but it should equal 51. So 63 parentheses 1 minus 0.1904 is 51. And that's greater than or equal to 10. So we're good. This one's good. It's definitely large enough. So now you need to check the other side. And we have 57 times 0.3684. And we know that that equals 21, and 21 is definitely greater than 10, so we're good to go there. And then we have 57 times 1 minus the 0.3684. 57 parentheses 1 minus 0.3684, close those parentheses. Then we get 36. And that's also greater than or equal to 10. All right, so the samples are large enough to use normality, and we've met all of our conditions. Our formula for the confidence interval is p hat 1 minus p hat 2 plus or minus z star p hat 1 times 1 minus p hat 1 over n1 plus p hat 2 times 1 minus p hat 2 over n2. All right. So next thing it asks us to do is to calculate z star. Well, z star is going to be inverse norm. Area is 1 minus 0.90 divided by 2. And we're working from the left. Second vars, inverse norm. Parenthesis 1 minus 0.90, close parenthesis, divided by 2. Mean is 0, standard deviation 1, left. And we get 1.6448. All right. So that's our z star, and now we can start plugging into our formula. So 0.1904, that percentage, 19%, were resistant. in 2014 minus the percentage is 0.3684 in 2017 plus or minus 1.6448. And 0.19, I'm going to go ahead and shorten this up just because I'm short on space. And then 1 minus 0.19 gives me 81. So this is 0.81 over my sample size of 63 plus, I'm going to round this to 37 because again, I'm short on space. So 0.37. This is going to be over 57. And 1 minus 0.37 is 63. And there we go. So we're going to go ahead and run this thing, and we're not going to run it with rounded figures. We're going to actually use our figures. So stat, test, 2 proportion Z interval, which is letter B. And we had 12 out of 63. Then later we had 21 out of 57. We want to run a 90% confidence interval. And we find out 0 is not in the interval. So we're going to we're going to believe that it's more resistant. So we have our interval is negative 0.3109 to a negative 0.045. The fact that it's negative means the second number was bigger. And sure enough, that 2017 was the second number. So 2017 had a larger percentage of plants that were resistant. All right, so now we need to write up our conclusion. And our conclusion is we are 90% confident that the true population proportion difference between resistant plants in 2014 and 2017, because that's the order, 2014 minus 2017, lies within the interval negative 0.3109 to negative 0.0450. All right. Appreciate you watching. I hope that helped. You notice 0 is not in the interval, so we know that things did become more resistant. This is a observational study, so we can't say it caused it, but it definitely shows a relationship. Thanks for watching. Hope to see you on the next one. Thank you.